what a Mott state is in real space. It's a very simple picture. But here, since we want to talk about the Fermi surface, we want to talk about superconductivity, we are interested in K-space. So what are the key features of a Mott insulating state, of Mott physics in K-space? In real space, we know that we must have an underlying lattice to get a Mott state. In K-space, that translates into saying that the underlying lattice will allow new low-energy scattering processes, possible low-energy scattering processes, which are unclap scattering processes, namely those that can conserve momentum only modulo reciprocal lattice vector. The second thing to get a Mott insulator, of course, is we should have a filling of around 1 electron per side, and that in K-space corresponds to a surface in K-space enclosing half of the Brillouin zone. So the conclusion is we should look for the onset of Mott physics at a surface where we have, so it is spanned by unclap scattering processes, elastic unclap scattering processes, and which encloses an area of half the Brillouin zone. Now, to see how Mott physics can come about, we have one particularly interesting example where essentially the charge gap is opened up at weak coupling, at arbitrarily small coupling. You have a charge gap without breaking translational symmetry, because of course the Mott argument has nothing to do with translational symmetry breaking. And that's this system which is ladders, which we call them Hubbard ladders when we put in the simple Hubbard interaction. The two-leg ladder is an example of such a system. We just have two rows of atoms with hopping T between them. Now, this problem has been studied by many people. I don't fear I have time to go into all the people that have contributed to this over the years. But when one looks at the simplest one loop, which is of course adequate at small u, one sees that the charge gap arises because at exactly half filling there are additional low energy elastic processes connecting the four Fermi points here. For example, a particle here and a particle here can advancement into this club of the 70. Oops, sorry, I'm getting into this club of people over 70. Those of you who have looked at the program, you will see my title of my talk today is a phenomenological theory. You'll see there's another phenomenological theory coming 2 talks down by one of the collaborators of Rama, which shows you that we are doing, both of us, in physics in the old-fashioned way. You know, actually trying to look at experiments and trying to figure out some consistent scheme that can explain these experiments. So that's the motivation for the talk I'll give today. And this exotic pseudogap phase was very nicely surveyed by the previous speaker, Shushitra Sebastian, so I can go over that pretty fast. But I will move on to our proposal to explain the pseudogap phase. And by say our proposal, this was done together with Kai-Yu Yang and Fuchun Zhang at the Hong Kong University, where I spent some time when the weather was nice in Hong Kong, and also it involved a lot of input from Robert Koenig and Alexei Sibelik at Brookhaven Lab, where I also spent some time when the weather was nice on Long Island. So then I will discuss the comparison to various experiments. Here I put up a theory for all experiments, but I won't keep you in suspense. I don't have you might have thought that since I'm scheduled right after the previous speaker that I'm going to explain all those beautiful experiments. I'll have to say, unfortunately, no. But this is clearly real progress, and it's time to have another go to see if one can explain them. And then I'd like to talk about the implications in this approach for what type of special excitations we would see in the pseudogap phase, and then discuss briefly just the general idea that the pseudogap phase is to be viewed as an unstable fixed point. So, of course, one of the things that attracts the theorists, especially to the high TC problem, is just how simple it is. All of these complications of multiple orbits and Hund's rule coupling and all that are not present here. It's just a simple square lattice, single orbital. It seems to be, in effect, dominated by a single plane, and so it's a single closely half-filled band. It's half-filled in the parent compounds, a strong on-site Coulomb interaction, especially in the parent compounds, so we can model it with some kind of single-band Hubbard model on a two-dimensional square lattice. Well, this is phase diagram you have seen before, and the pseudogap phase, as you heard from the previous speaker, is this phase that sits between the region out here where we have this full Fermi surface that's seen in quantum oscillations, as we also heard, or also in photo emission, and over here where we have this Mott insulator with no Fermi surface at all. So the approach I'm going to be taking in this talk is to look at what happens in this intermediate phase in terms of how the full metallic Fermi surface here is reduced as we head towards the Mott insulator where the Fermi surface is completely lost. As we come across here, the Coulomb interaction on the low energy scale is going from something that we can treat perturbatively over here to a situation where it has completely reorganized the low energy properties. Now, one of the key questions that has been raised is about the importance of possible translational symmetry breaking, because in some cases there are examples of translational symmetry breaking in this pseudogap phase, but if one looks for the cleanest underdoped samples, such as this 124 or this sample we heard about earlier, these don't show it. For example, this is this is NMR on the 124 or 248 that was shown on the one of the graphs in the previous talk. And here you can see the different oxygen lines. This is two oxygen sites, 2 and 3 are the planar oxygen sites. There is beautifully narrow lines because this is a stoichiometric compound, this material here, and these are small splitting of the planar oxygen sites because one of these sites sits over the chains and the other sits over the space between the chains. But there is no sign of any charge density wave formation, which of course NMR is very good probe, or even more so of a spin density wave, which NMR is an even better probe. Now, the anomalous properties were first seen in the night shift on this material and related underdoped materials, and this night shift is very interesting because it starts to drop already at room temperature, quite in contrast to, say, 123 oxygen 7, where you have a Pauli-like susceptibility till the onset of the superconductivity. It drops continuously with no sign of any phase transition, no sign of any jump or kink, and here is the onset of superconductivity. Here you can hardly see it on this particular curve. So the value that is reached down here is almost 80% loss of the value that was up here. So this indicates that something more than just antiferromagnetic correlations are going on, that some form of spin pairing is going on in characterizing this pseudogap phase here. So the spin susceptibility is well below that, and that, of course, makes a connection with Anderson's famous OVB proposal. So, of course, the most dramatic effect was the effect discovered by the group at Argonne that in photo emission that the full Fermi surface in the pseudogap region is reduced to a set of arcs centered around the nodal direction here. And this particular data is taken from Ziyech Shen's group. So this is the ARPES signal within plus or minus 10 millivolts. The ARPES signal, of course, measures the imaginary part of the Green's function then around zero frequency. And the question is, how do we understand that this full Fermi surface that's seen in the overdoped region is reduced to this set of arcs? Well, there have been a number of proposals. The initial proposal was what nowadays people call the one-gap scenario, namely that the Cooper D-wave pairing gap, which opens up on the full Fermi surface, with characterizing an energy scale much bigger than the transition temperature because of strong phase fluctuations, because of the reduced superconducting stiffness, reduced TC. So this would say the near antinodal regions where the D-wave superconducting gap would be maximum. If this is much bigger than TC, it could survive into the normal phase. Now, the alternative is a two-gap scenario, which is that the pseudogap is an insulating gap opening up near the antinodal K-points, such as a OVB gap, opening up due to particle-hole and particle-particle scattering. This is the proposal that I will be following here. And the simple ansatz we make for the Green's function is based on this type of physics, a simple guess for the possible form for the Green's function. And of course, since it's phenomenology, the proof of the pudding is in the eating, so we have to test it against various experiments and see how well it can do. And so that will be the goal in this talk. Now, we all, of course, are very familiar with hopping, but still we always have the following property that any point on this surface, it forms a star of 8 degenerate points by tetragonal symmetry. And these surfaces then, these points are connected by a network of scattering, not just particle-hole scattering, as would be the case when we worry about antiparamagnetism, but also particle-particle, similar Umklapp processes to the ones we have in the two-leg ladder, like this process. Also, it changes the momentum by 2 pi, so it's an alloyed process. In fact, these 8 points, the matrix of scattering events that connect these 8 points are very similar to that in the case of the two-leg ladder. So this was the motivation for looking at a formula for the self-energy, which was related to the two-leg ladder, but then which would open up the gap along this Umklapp surface here. And the form we came up with about 5 years ago was the idea that we would put in a self-energy, which has a pairing form, but the energy in this self-energy here in the denominator of the self-energy would not be just any old energy, but would be go to zero exactly along this Umklapp surface. So it's like a pairing form, but the pairing is being tied to a specific surface in K-space, which is a surface which is spanned by these elastic Umklapp processes. Because if we're going to get an insulating form of pairing, we clearly must have the pairing tied to a surface in K-space which is fixed by the lattice, and it's not simply related to the Fermi surface. If it's a Fermi surface, then we're talking about a superconductor. So we came up with this form and proposed that this anomalous self-energy would keep its form even when we dope. And that goes back to work with Robert Koenig and Alexei Cervellik on an array of two-leg ladders where we could show for a specific choice of interladder hopping that one could justify a form for the self-energy of the individual ladders remaining untouched when we introduced longer range hopping between the ladders. So this is the form then. We have this simple pairing self-energy but fixed at a specific surface, and here we include the next nearest neighbor, etc. hopping. Now, the form is also, a number of these factors are taken from original work related to the OVB state, going back to the early days of ITC, in an attempt to put in, if you like, strong coupling corrections into this form here. So this anomalous OVB gap parameter shows to be strongly hole density dependent, maximum in the parent compound, and then vanishing at a critical density, say, of 20%. Now, this form then, when we look at what it gives us for the dispersion in K-space, you see this form here, the Green's function at omega equal to 0. At omega equal to 0, our self-energy vanishes along this line here. That's what we chose, this just nearest neighbor form for the energy dispersion in the denominator. So it vanishes along this line. I mean, the denominator in the self-energy vanishes, the self-energy diverges, so the Green's function itself has a 0 along this line. So this zeros then should be included when one comes to calculate the area enclosed in K-space for the Green's function omega equals 0 is positive. This is the Luttinger sum rule generalized by Jelasinski. So this form here then is fixed because we've kept this divergence fixed. And what we find is when we introduce some holes, the holes go into this nodal region because, of course, this is the form where our D-wave form for the OVB gap vanishes exactly along this nodal region. So these pockets then expand, and finally, when this OVB magnitude of the gap is small, you get a small region with additional electron pocket, and these coalesce, and you get back to the full Fermi surface. Now, an interesting feature of this is that the quasi-particle's spectral weight varies very strongly around this pocket and is concentrated essentially on this front edge here, which of course makes it look like the photo emission, which looked like arcs. Now, the photo emissions, since the original days, there's been recent interesting results from the group at Brookhaven, and a few years ago they published these scans where the interesting thing that they did was they looked at the normal state, of course at a fairly high temperature of 140 Kelvin, and then there is a tail above the chemical potential from the width of the Fermi function. So they divided out this Fermi function to get in spectra then not just below the chemical potential but also above it. And here is an optimally doped Biscoe sample. Here are some cuts along nodal and to near nodal directions. You see particle hole symmetry. You see something that looks like a quasi-particle peak just going straight through the Fermi energy. But when we took an underdoped sample, they saw something quite different, namely that as they moved away from nodal, what was nice and particle hole symmetric now started to get cut off, and when they went out here, the main part didn't even reach up to reach the chemical potential. So they saw particle hole asymmetry developing along that arc in the underdoped region. Now, this is the more recent results published earlier this year in PRL, where they used image enhancement, modern image enhancement techniques to enhance the signal, and here they saw actually not just a cutoff on the signal, but a form of bending over, as you can see here, for a set of cuts, namely out here at the edge of the pocket. Now they lose intensity after they go through the maximum, but the maximum that they see, interestingly, are not situated along this anti-ferromagnetic V1 zone boundary or along the zone clap surface, but halfway in this sort of the center of such a pocket. So they can measure then up to this point too, and then they extrapolate using a simple parabolic extrapolation to get a possible second crossing of the Fermi energy here at this point 3, which is just then inside this V1 zone. And you see this form that we have also has this loss of weight. This is just like in about the Lyubov pairing quasi-particle. When you go through the maximum in the Lyubov spectrum, you lose weight rapidly on as you cross the maximum. So the form that this pairing form that shows has exactly this weight loss, and so it's very nicely consistent with these ARPES data. And this just then shows the area of these pockets and the relation of that to the doping. It scales nicely with the doping. So this recent then the ARPES data from the Brookhaven group, Hongbo Yang and Peter Johnson and John Rameau agrees very nicely with this form for the Green's function, this ansatz. Now there are many more experiments that one can do when one has a simple form like this, many more experiments that one can analyze, and particularly Jules Cabot and Elizabeth and Nicol up in Canada have been busy doing this for a whole series of experiments, Raman scattering, specific heat, infrared, conductivity, penetration depth, and but I won't go through them here. We recently prepared a review on this. It's on the net and should come out soon, and reports on progress in physics, and you can follow up on that if you're interested in this review. Let me just say a few words about the last topic that I have down here, which is Andreev tunneling, because that bears a lot on this question of whether the gap in the antinodal region is a superconducting gap or some form of insulating gap. The idea goes back to earlier work by Guy Deutscher, which is to compare the tunneling spectra for Andreev's tunneling and for regular single particle tunneling. The Andreev tunneling is indicated here when a particle comes up and a Cooper pair penetrates into the superconducting sample with an emission of a hole backwards here to conserve charge. Now this process requires transparent barriers. On the other hand, if you have a high barrier, this process, which involves two particles moving through here, is reduced in amplitude, and you're dominated by simple single particle scattering. And now normally the energy the voltage range over which you see this Andreev scattering is the same as the voltage range where you see the superconducting gap where there is no single particle tunneling. The Andreev process here is at small voltage, and then when you reach the voltage corresponding to the superconducting gap, you see the single particle. And this then can be calculated directly using this form, generalizing it to putting in by hand a D-wave pairing interaction as well. So this is just the comparison for the underdoped. In the overdoped case, the energy scales in both the Andreev or transparent junction and the Gieve or single particle junctions are the same. But here in the underdoped region, the experiments on the Andreev are just plus or minus 20 millivolts, whereas out here these maxima in the single particle are plus or minus close to 80 or 100 volts. And this then is the black are experiments, and the red the red is the superconducting, in the superconducting state. It's the conductance in the superconducting state. And you see here the red, well, here we have the red in the superconducting state does show additional peaks here in the presence of the small corresponding to the superconducting gap just on the arcs, whereas the antinodal region here gives us these peaks which persist into the normal state shown here in blue, and this is a comparison with an STM spectrum from experiments of the Seamus-Davis group. So you see, the key point is that this voltage scale here for Andreev is much less than the voltage scale corresponding to the separation of these single particle gaps. So how much time do I have? 10 more minutes. Okay, so I'd like to come to talk about excitations in the pseudogap as the pseudogap ups, which are suggested by this phenomenological form. Now we made the the analogy to the two-leg half-filled Hubbard ladder, and of course in that case we know what excitations of the low energy excitations are two forms. There is a triplet magnon excitation at pi inside the gap, and a Cooperon, or a excitation of two holes or electrons inside the gap. Now, so the question then is what we should expect in the two-dimensional case. Well, then recently with Andrew James and Robert Konek from Brookhaven Lab, we just put on the net a calculation of the spin response within this model, and just using a RPA description where the non-interacting, so to speak, chi, the bare chi here, is chosen by a product of these anomalous, of these ansatz propagators. And there are three parts to this spectrum. At low energies, there is at low energies, there are these transitions between these pockets, and these give rise to spectra which are slightly away from pi, and in fact, even the form in K-space, namely that the maximum intensity is along the crystalline axis, follows from the calculation of the spectra in the superconducting state. Then we have this triplet magnon mode, which comes in here around 30, and then we have an isotropic continuation of this magnon mode to higher temperatures, the higher energy, sorry, and that agrees quite well with the experiment here. These are a set of experiments from different samples, and they are scaled by a number j here so that they all lie on the same curve. So this, these calculations describe quite well the magnetic, the spin response in the pseudogap phase. And very recently there were new data published on Rick's experiments in Nature Physics. This is now the high energy region above 100 millivolts, and the false color background is this same calculation extended to higher energies, and these dots here are the points, and you see that again the existence of this mode here, which is kind of a mode in between the energy gap of the lower and upper pairing bands that we have, agrees quite well with the form of it, agrees quite well with the experiment. So let me turn to another issue, because it's long been questioned about whether the pseudogap is a friend or a foe of superconductivity. Now, I mentioned earlier that the analogy with the two-legged ladder would lead us to think that maybe there is some kind of Cooperon excitation occurring in this pseudogap phase. Actually, there's an interesting model, very simple model, put forward about 10 years ago by Philippe Nozière, who considered a model with a 2D semiconductor with a simple S-wave attraction treated in BCS theory. But the point is, he varied the size of the semiconducting gap. So when this vanishes, it's just a simple metallic state with a constant density of states, because it's in 2 dimensions. So you introduce an attraction, and you get a superconducting gap and some superconducting stiffness. Now consider what happens when you open up the semiconductor gap. Well, initially, when the semiconductor gap is small, the system still stays superconducting, but it reduces the pairing amplitude. This delta here is reduced. The stiffness is reduced, and the single particle gap is also reduced. Eventually, when this semiconducting gap is big enough, we make a transition to a semiconductor in the normal phase, and now the single particle gap here, the normal phase, of course, is now the stable phase out here, this standard semiconductor. The single particle gap is just the semiconducting gap. So you see the single particle gap is continuous and remains finite as we go through this quantum critical point. Now, if you take a look what happens in this semiconductor actually then supports a Cooperon, or a bound state of 2 charge carriers in it, which then goes to 0 at the quantum critical point. So remembering that in the antinodal region, as we go through the quantum critical points separating overdoped and underdoped, the single particle gap in the antinodal region, of course, stays finite and continuous, doesn't go to 0 or anything like that. So that suggests that one should look for some kind of Cooperon excitation accompanying the opening of this insulating gap at antinodal. So if you would get a picture like this, and the model like that was actually analyzed by Kai-Yu Yang with using sophisticated Monte Carlo methods earlier this year, a model with pockets coupled to a finite energy Cooperon. Well, here, the existence of such a Cooperon, of course, helps the pairing, because in addition to, if we look in the Cooper channel, in addition to simple exchange of some mechanism, the bosonic mechanism, one has these sorts of graphs where one scatters resonantly into a Cooperon and out of it again. So these additional graphs here then support the instability, pairing instability. So you can get pairing on pockets induced in addition to any sort of regular interaction, also by the virtual transitions. And in a specific model where that type of physics appears, where it was published last year, it's a 4-leg ladder model where 2 of the bands are gapped but have a Cooperon, and 2 of the bands, the holes are, the doped holes are just in 2 of the central bands. 5 minutes, okay, I'll be finished. So the question is, how can one see that? That's a very interesting but difficult question. One effect that we have been following up on is this. There have been various reports of so-called joint proximity effects in the cuprates. I mean, this, for example, is work also done at Brookhaven Lab, where they had 2 LASCO superconductors with 45 Kelvin transitions as leads, and in between a weaker doped LCO, oxygen doped LCO, which had a TC of only 25 degrees. And here you see they saw this big tail in the Josephson coupling between the two 45-degree superconducting leads. And this is a recent, but not yet published work with these people in Hong Kong, Kai Kun Huang, YQ Chen, who are co-workers with Fu Chun Zhang. So here is the dots are our calculation here, and the line is the experiment. And what one does find then is that one can get a tail up to extending considerable distance above the transition temperature in the barrier, which in this case was chosen as 25 degrees in line with this experiments. Now we use then this wire Z-type propagators with an additional attraction in the D-wave channel to get the superconductivity, but in the normal state of the barrier, then above the 25 Kelvin, this form here does give one just such a Cooperon. This is the energy of the Cooperon dispersing downwards, namely as it moves away from the chemical potential up to finite energy as one goes further above the superconducting state. Well, just in the last couple of minutes, I would like to make us shift gears. I mean, I justified the possible form for this Green's function from recoupling and looking at how the Fermi surface, the full Fermi surface, might be truncated as we increase the Coulomb interaction. But Patrick Lee pointed out to me that there is actually a simple way to derive this from slave boson description of the TGA model. This is the standard TGA model. Then one divides this, introduces this factorization, slave boson factorization. Then this spin-on term here, this Heisenberg exchange, depends only on the spin-ons, and one gets a Green's function for the spin-on or fermionic spin-ons, which then has an energy denominator. One does, in the standard way, decouple it in particle-hole and particle-particle channels. One has this similar form for the self-energy. On the other hand, if one looks at the bosonic Green's function and makes the assumption that these are essentially condensed, but almost condensed, if going back to work of Tai K. Ing, he makes this simple assumption for this form, and then one looks at this hopping term. Now this hopping term, the C dagger C, when we write it out in this notation here, is F dagger F, B dagger B, so that gives you an interaction between the holon, the bosonic holons here, and the fermionic spin-ons. One simply calculates then the letter graphs of these form here, then you get exactly back to the similar form that we had guessed at or proposed based on the recoupling approach. And then just one last remark is this question of Cooperons is whether this makes sense in a TGA model. In fact, the best exact diagonalization on finite size clusters are on 32 side clusters with two holes, and they were done by Pac Young and collaborators in Canada, and there's a very nice analysis by Thomas Meyer, Didier Paul-Blanc, and Doug Scalapino recently. Now this cluster is very nice because it has the antinodal pi 0 and the nodal pi half. And the ground state that one finds for two holes in this cluster is a competition between two different states. One is a bound state of two holes, a Cooperon with D-wave character, and that's the energy of it here. And if you choose J over T over third, it's still bound, it's still the ground state for the case of the 32-side cluster. But if one expands to infinity, it becomes an excitation, and the holes instead go into these nodal points at pi half. Now, at the time when they published this these authors concluded that this means there's no superconducting state. No, the TGA model is doesn't show automatically superconductivity, but I think that's a bit too pessimistic, because if we go to an infinite system but keep a finite hole density as we go to infinity, then we will occupy not just these exact nodal states for the holes, but a small region of K-space near that. That will allow us to coupling then when we move away from nodal to the Cooperon. So we see that these calculations here also support the idea that there could be a Cooperon existing in this strong coupling model. Well, I will finally conclude here. So this this ansatz gives us different behaviors. Of course, a nodal and antinodal interpolates between them. This different behavior, of course, is consistent with lots of DMFT results by these authors here. The pseudogap is how should we look upon the pseudogap? I think that the correct way goes back to Phil Anderson about 10 years ago, that the supergap is an unstable fixed point, similar in the way that the Fermi liquid state in the metal is. That's to say, it's stable for a while, but on the true low energy, low temperature limit, it may well be unstable against superconductivity, magnetic order, etc. So it's an unstable fixed point, but at low energies then there could be some further instabilities. Then the superconductivity in the pseudogap is not quite a friend or a foe. But it is supported that as the insulating gap opens up in the antinode, there can be a Cooperon mode which will help induce the superconductivity in the fermion pocket, and magnetic order can be generated through the coupling through the triplet magna node. And of course, the big thing that we're missing is this beautiful explanation for this beautiful magnetic field experiments, quantum oscillations. But after this beautiful talk, we're motivated to go back and try harder. Thank you very much for your attention.
And so, in paneling, did you talk about?
Well, it doesn't give an Andreev effect. I mean, in the superconductor, you have like a Bose condensate of these Cooperons, and then you can get a coherent tunneling amplitude back.
But some signature should be there.
Well, maybe something, but maybe something small. Yeah.
Called Luttinger-Dzelashinsky theorem.
Yeah.
Just for the record, Luttinger, of course, a theorem as to the Dzelashinsky, but you had in mind that when green function have zero, one can just add to the Luttinger sum rule the area of zeros.
Yeah.
This is not correct. At least in the simplest example, very similar to what you use. The point is that in the expression which Luttinger will use, it's assumed that series which you do expansion of self-energy and so are convergent. And obviously for the self-energy which has zero, they are not convergent. When you, at least an example when one can follow everything, see what is going on, then also what one sees is that with the zeros you get to some wrong branch of just expression. If you do, because of the finite radius of conversion, if you take correct one, then what come out is that eventually these zeros drop out. They exist in some intermediate calculation, but they eventually dropped out in the final expression. So there are not such a simple formula like just pose plus zero. This is incorrect, at least for the most transparent model.